I'd like to show you a project Esri developed in conjunction with the RAY, a nonprofit organization that supports a variety of innovative projects to expand access to alternative energy. One of their goals is to encourage state departments of transportation to put solar in their highway right-of-ways, which are usually undeveloped areas. The RAY partnered with the University of Texas at Austin to investigate the potential for solar installation in right-of-way areas. The university developed a national-scale analysis which involved using artificial intelligence to detect highway interchanges. And then they classified the interchanges, such as diamond or cloverleaf, and estimated the acreage and calculated the solar potential and electricity value for each location to give the states an idea about how much energy and income they could produce in their right-of-way. I'd like to show you how ArcGIS can extend this research and provide more detailed information on developing solar in highway right-of-ways. We built on the work done by the University of Texas and refined it using GIS analysis and detailed spatial data from Iowa, who's published their right-of-way on ArcGIS Online. Iowa has over 230,000 acres of right-of-way land. We were given some analysis criteria. The right-of-way had to be within 5 miles of an electric transmission line, outside of national parks and national forests, outside of protected areas, outside of urban areas, away from natural gas, HGL, and crude pipelines, or 500 meters from a pipeline, 20 feet from a rail line, and outside the highway clear zone, which is 40 feet. So let's start with the electric transmission lines in Iowa. And this is the area within 5 miles. So we have to stay within the green area. For our exclusion requirements, we had to be outside of national parks and national forests. For this, I chose a federal lands layer from ArcGIS Online. Iowa has a little bit of fish and wildlife land, a small national park, and some Department of Defense land. So I omitted all of that. We also had to stay away from protected areas. I chose a critical habitat layer. These large patches are actually a protected fish. So instead of omitting the entire area, I buffered the waterways by 100 meters and just removed this land. We have to stay outside of urban areas. This is a city boundary layer. And these are the pipelines, the crude oil, HGL, natural gas, and petroleum products. We have to be 500 meters away from those. And these are the railroads. We have to be 20 feet away from those. And if we merge this data together, we can create our exclusion area layer. And we have to stay outside of all this area in red. All of the data for these criteria were published on ArcGIS Online, and most were at a national extent. And you can add other layers to include or avoid as desired. But that's not all that needs to be excluded. We need to remove the highway clear zone. The area in blue are the detailed right-of-ways that Iowa DOT, Department of Transportation, publishes. They also publish the street center lines. I needed road widths, so I buffered the center lines by the number of lanes to get this result. And then I buffered that by 40 feet to get the highway clear zones. And then I erased those from the right-of-way to get this area in blue. Now let's look at the criteria again. We have to stay outside of the exclusion area in red. We have to stay inside the inclusion area in green. And so areas like this and this will be omitted. And this is the result. But then we found another issue. We found some thin strips of land, and we know that the University of Texas document said a row of solar panels takes 30 feet. So I omitted any strip of land that was less than 60 feet, assuming a row of solar panels and then some area around it for fencing and maintenance. And this is the final result. And we can calculate the solar potential for any of these parcels. And we can do that calculation for all of Iowa. Iowa has over 38,000 acres of right-of-way land available for potential solar installations. Using the rule of thumb calculation, where 1 megawatt of electricity can be generated on 5 acres of land, Iowa has a solar potential of almost 5 million megawatt hours per year, valued at over $400 million per year. This is a GIS analysis that most DOTs can do using their own street center line and right-of-way data combined with data published on ArcGIS Online. Using GIS spatial analysis and a robust spatial dataset, we're able to get a more accurate picture of the available land that the state could use for solar installations. So this analysis is based on an acreage calculation, and we wanted to go further and analyze the actual solar radiation values. So we picked a study area, an 80-mile stretch along I-80 in western Iowa. Using solar radiation analysis tools in ArcGIS, we can be even more accurate with our solar potential calculations. To give you some background, our solar radiation tool uses an elevation surface to define the landscape. It can either be a digital elevation model, or DEM, which only shows the ground surface, or it can be a digital surface model, or DSM, which includes the vegetation and any structures on the landscape. And we can blend this data together with the imagery to get a more realistic view and to help us understand the terrain. So I ran the solar analysis tools using the digital elevation surface without the vegetation, and you can see the areas in red are high solar radiation values, mostly on the south-facing slopes, and the areas in blue are lower solar radiation values, mostly on the north-facing slopes. And we can compare this to the same analysis run with a digital surface model with the vegetation. And you can see how the vegetation influences the solar radiation over the area. But not all of the solar radiation is usable because current solar panels have about a 20% efficiency rate for converting sunlight to electricity. I calculated the new solar potential for the panel efficiency rate and clipped the data to the right-of-way. Then I summed the adjusted solar radiation values within each polygon to get the solar panel potential. So this is a 7.4 acre polygon parcel, and adjusted for the 20% solar panel efficiency rate, if this polygon was cleared of vegetation using the digital elevation surface, it has a solar potential of over 6,000 megawatt hours per year, valued at over $500,000. If the vegetation remains using the digital surface model, the usable solar potential and value is decreased by more than half. So there can be quite a difference in value between the vegetated land and the cleared land, and that's important to know for our project planning. So we have a lot of land to choose from. And to help us prioritize the land, we can use a suitability model. In our model, we favored areas with high solar radiation values, southern aspect or south-facing slopes followed by eastern and western aspect, and then low to moderate slope for ease of installation and maintenance. And here's the result of our suitability. And the areas in darker green are the most suitable areas for solar panel installation. So let's focus on this area. Looking at the data in 3D can give us more information about the analysis. And to understand the landscape better, we can turn on the LiDAR point cloud to see the vegetation. So let's look again at the digital surface model, the solar radiation calculated with the digital surface model using the vegetation. We can swipe away the trees, and now we can understand the pattern in the data. We see how the trees block the sun. So let's look at this south-facing slope. It's suitable for a solar installation. And to refine our analysis even further, instead of calculating solar potential based solely on the landscape, we wanted to calculate solar potential based on solar panel installations. I've already added a solar array to this hillside, and this project has over 35,000 solar panels that each can generate 300 watts. And combined, they have the potential to generate 13,000 megawatt hours per year of electricity, valued at over $1 million, just this hillside alone. And it can power up to 1,200 homes per year. And using the EPA greenhouse gas equivalency formulas, the carbon reduction from this solar installation is equivalent to avoiding over 9,600 metric tons of carbon dioxide emissions, which is also equivalent to not burning 10 million pounds of coal, or getting more than 2,000 cars off the road each year, or not using 1 million gallons of gasoline, or the equivalent of the carbon sequestered in over 11,000 acres of forest. So let's go farther down the road. This is also a suitable hillside, and I've added a solar array to this. Let's zoom in to take a closer look at the solar panels. Creating a digital twin like this can help us analyze and plan the development. It can also help us find situations that might be less desirable for the community. For example, at the top of this hill is a scenic overlook. The solar panels are in the right-of-way, but let's see how they might affect the visitor's view. We have an interactive viewshed tool, and say the visitor is 6 feet tall, and we want to look all the way around 360 degrees, and we want to look out 5,000 feet. We'll put the visitor here on the sidewalk. What we're seeing is the area in green is visible to the observer, and the area in pink is not visible, and we can see that the solar panels block the entire view. So what would happen if we took off a couple of rows of solar panels? What would happen to the view? So that helps. Now we can see the high hill, but we can still see a shadow of the solar panels that are blocking our view. So let's take off a couple of more rows. That's great. So now we can see the entire view, and we can zoom down to ground level to confirm that we don't see any of the solar panels. These are the panels that don't block the view. And now we can quantify the trade-offs. For our decision criteria, we can calculate the full panel installation scenario, the preserve the view scenario, and calculate the difference between them. And these are powerful tools for the planning process. They can inform and improve decision making, enable community engagement, and help us understand the trade-offs. So let's go to another area. Another interesting thing I learned while working on this project is that Iowa is already active in renewable energy production. They have a lot of windmills. This winter, my husband drove across Iowa, and I asked him to take some photos for me. And he stopped at this rest stop that turned out to be really cool, because its theme is alternative energy. And you see this shadow here? That's a shadow of one of those giant turbine windmill blades that they have on display right here. And they have a plaque with information about it. And since this rest stop is already promoting alternative energy, this would be a great example of installing solar to generate electricity for the rest stop and to inform the public about the benefits of solar power. So then there's an area to the left here that we could install a solar array. So I'll start editing, and we have a new tool that allows us to add multiple features quickly. And we know that a row of solar panels is 30 feet across apart, so we can just click those in. And that's too close to the road, so we'll back it off one. And then I know I've sized my solar panels, my symbol, to be 4 meters wide, 4 1-meter panels across. And I can just click those in. And that's probably too many because we want people to still enjoy the grassy area, so we'll back that off. We can apply that. And because we're working in 3D, we want the features to be on the ground. So we'll run a tool to get the Z value from the elevation surface. And just like that, we've created a solar array. But we also want to know how much electricity it can generate. So we can run another tool to calculate that. So we see that this array has 360 solar panels. It can generate 128 megawatt hours per year of electricity, valued at over $11,000. And it can power up to 12 homes, or possibly the entire rest area. And this solar array is the equivalent to the carbon reduction of 90 metric tons of CO2 emissions. We've seen that GIS can be used in many ways with solar development, from determining available land for installations, analyzing solar radiation on the landscape, planning installations, and community engagement. And we hope this analysis will help the array achieve their goal of promoting solar installations in the highway right-of-way. Thank you.